As a reminder, like all my other classes, this one is licensed Creative Commons. It's public released. It's available in my transfer folder in public release form. And actually, I was just going to throw this in there, but let's see, I did just make, so the point of getting them public release was to get other people to start teaching them. And so the point is, once you know this material good enough, feel free to take it and teach other people in your department or section or whatever. And so I do have the slides and everything available online at OpenSecurityTraining.info. And so that's going to be, we're going to be grabbing other people's materials from other classes and just soliciting volunteers from other people in the industry. So, thank you. All right, so first some credits for people who've contributed information in this class. Or help review it, like my wife. But the point here is, if you have any ideas, if you bring up any questions that lead to new information that I hadn't previously covered and stuff like that, I'll credit you for telling me stuff that I incorporate into the slides. So later on, there's some material by Rod Kahn where you'd pointed out that how Google's native client or Macro browser protection software or browser plugin protection software, it uses some of the segmentation type stuff that we're going to learn about today. And then Christine Jones, just in the intermediate class this year down in McLean, she pointed out some good information about how the global descriptor table, which we'll learn about later, how that works on Linux, and that sort of brought up a good point about how it probably works on Windows as well. I haven't got around to confirming it yet, but when I get there, I'll point this out. I haven't put that into the slides yet. So at the beginning, as usual, we're going to go around the room and introduce ourselves. It's less for me because I know most of the people who've taken the classes. It's more for introducing yourselves to the other students. Obviously, if you're all in the same class, you all have some common interest in this. So probably good to know who else has common interest throughout the company. A lot of you have, but kind of the point with this class is that we are trying to build up. So the point was, we know that we have lots of people who want to do malware analysis, reverse engineering. So actually, separate malware analysis from reverse engineering because, for instance, I do reverse engineering on the kernel, for instance, but there's a world of difference between reverse engineering just some regular compiler-generated code and reverse engineering malware, which is actually trying to screw with you. So I think those are sort of two different things, but the point was we knew that there's people who need to know these sort of skills, want to know about exploits, reverse engineering malware, and so this class is going to get you far there. It shows some. I think in a newer version of this, I have a recommended line. Yeah. So, anyways, the point is, there's a lot of stuff you need to know in order to get to those final states. This is trying to give you a more gradual transition there, and so the more of the blue stuff the easier it is to go to the future ones. Yeah, and actually, I didn't. This is an old slide, so actually, reverse engineering is approved, right? It's going to be approved. This will be in. So that is approved actually, and vulnerabilities and exploits is approved as well. Corey's going to teach that in first week of June. But yes, malware analysis, trying to target for next fall or something, fall, winter, depends on, again, math schedule. And advanced x86, probably maybe winter, maybe spring next year. But that's all I'm going to be teaching next year. So all the ones that are currently blue will be on video available next year. I think on the reverse engineering and vulnerability exploits, because they're new instructors, they're not necessarily going to have videos on those this year. Oh, that's a good point. Rootkits I haven't offered yet, but that is going to be first week of April, I believe, and maybe third week of April. And Life Planners is one that we already offered. All right, I think we got everyone for introductions. So we're really, compared to some things like Life Planners where we were trying to hit like a ton of things, ostensibly we're only covering a few topics here, but we're covering them very deep, so there's a lot of information. So part one is going to be segmentation, which is memory segmentation. Is how x86 can chunk up memory and say that, here's one memory segment and it's code, and here's one segment and it's data, that sort of thing. Paging is how they go finer granularity than memory segments. Memory segments can apply just to actual physical memory, like sort of one-to-one. Paging is when you start having virtual memory, and so we'll get into that later. Interrupts. Oh, and I should say that segmentation, actually, the reason we're doing it first is because segmentation kind of underlies everything else. So you'll see the effects of segmentation on paging later. You'll see the effects on interrupts and maybe debugging, not so much debugging. Kind of, but not really. So at the very end, we're going to start getting into the stuff which is definitely, so the first three are sort of, for instance, for the malware analyst type people, the first three are things which are good for, understanding the system, good for reversing kernel malware and stuff like that. And then the part four is going to be some of the very practical stuff about, understanding how your tools work, understanding how debugging works, input, output, and miscellaneous. Speaking of miscellaneous, if you have questions, you need to ask them right away. This is definitely, again, one of those classes where we're just really hammering on content. So if you get lost and if you don't ask questions and reiterate your understanding and say, okay, so wait, was that again the logical address goes to linear address, how, blah, blah, blah. Right, so there's going to be lots of terms and all that. So definitely, please ask your questions when you have them. People on the phone, just, shout out, interrupt. I'm not going to get offended. And yeah, if you're checking the web and, reading email in class, that's a great way to get lost. I definitely, when we have, full classes, I always see one or two people who, they're so busy, they got to keep checking their email, they get lost, and they take it multiple years in a row. So how we're going to be, doing this, since this seems to be working right now, the first 2 hours, we're going to go 2 hours while I have your attention, while you have energy, etc. 2 hours, 10-minute break, and then it's another I think it's 2 hours, 10-minute break, and then 1.5 hours, and then lunch. And then after lunch, you'll be falling asleep. Please eat a light lunch so that you don't fall asleep. But after lunch, we'll take a break every hour, 5 minutes. All right. So the basic scope of the class, like the intro x86 one, is that we're only talking 32-bit stuff, not 64-bit, or not 16-bit as well. I think in the advanced x86, we're going to take this back and learn some 16-bit because that's relevant for BIOS, and some 64-bit as well, just for purposes of explaining what all is there. I'm not going to deal with floating point stuff again, because you don't really see that much unless you're analyzing 3D drivers or something like that. And so really this class, unlike the intro class where the point of it was to get you the basic instructions so that if you read small snippets of assembly, you're comfortable with them. This one is going to focus more on the underlying architectural issues that could potentially have effects when you're analyzing things. There will be a few new instructions, but they're really just, some of them are just thrown in because they are other things that you may see in the wild and it's relevant for you to know. So the main thing I'm hoping you get out of this class is a better understanding of how OSs use the x86 architecture. So we're focusing on Windows in here, but really everything we're learning relates directly over to Linux type things. There may be differences in implementation, but fundamentally OSs and virtualization systems, they both work with what they've got, and what they've got is whatever Intel gives them. So they only have whatever capabilities are exposed by the hardware, and so knowing those capabilities means you can look at this OS and that OS, and on both of them, how the interrupts are working. On both of them, they're using or not using segmentation, etc. And especially since, we're coming at it from my own security. While these classes are, supposedly meant to be, generic and help, developers and security people and everything, mostly I've only been getting interest from the security people. So at this point, we just abandon all context of genericness. And most of our examples are security examples. So it's especially good to know where the hardware is actually exporting the security, how the hardware is enforcing the security, rather. And yeah, just to get you curious and want to keep digging in more for whatever I don't really cover to your satisfaction. All right, so before we begin, we're going to do a little quick quiz on the instructions that we learned in the previous class. So, Matt, what's that first one?
You know what? Nothing. Add something, something. I can't remember.
Yeah, you know I was going to ask what the, anyone else remember what the underlying instruction actually is for no-op? So we said that's actually a no, it's, you know, no-op is a mnemonic, but in reality the hardware is doing a particular one, yes?
Is it adding to the next instruction register?
Nope. It does do that. I mean, it obviously just, it skips it and it goes, you know, one instruction forward. But, do you have a guess there?
I was saying it's one of the arithmetic operators, but now I can't remember which one.
It is not one of the arithmetic operators. How about anyone on the phone? Except for, oh, there we go. Jessica, nope, Jessica's wrong. Anyone else? Remember what the underlying thing with no-op is? Remember, the only reason we covered it is because generally people who know x86 have never looked up the manual page for no-op and they don't know this little bit of trivia.
Isn't it
So,
exchange EAX?
That is correct. Who was that? Adam?
Yeah.
All right, good. Yes, it's exchange EAX. So take a register and you exchange it in the other register, which is itself, and therefore it does nothing. All right, good job. How about, all right, push pop. Yep. So what are the side effects of adding the value to a stack and removing it? Side effects in terms of changes to registers. Yep, so remember that the stack grows towards low addresses, so on pushes, you're putting something on the stack, you're moving the ESP lower, so it's decremented. And when you pop something off the stack, you're taking it back off. The stack is getting smaller, but it goes towards positive addresses, and so it's incremented. All right, call and return.
You resetting the EBP to the appropriate place and then jumping into the right code?
Not quite. You're thinking definitely of the exit sequence, but that exit sequence is typically multiple instructions or some other instruction which is on the slide. But no. Or can you find the other instruction, which is the thing which actually replaces, restores the EBP? That's actually the leave instruction at the very bottom. So the leave instruction we had said was actually kind of like two instructions we typically see at the very end of the code. It takes and it moves ESP to EBP, or moves EBP to ESP rather, which, like we said, if you take, EBP is always stored at the top of the stack frame, and ESP is down here, you know, growing and shrinking or whatever. And we said if you take ESP and you put in the address of EBP, you're setting ESP back up here, and it basically is wiping out all of your local variables. You're setting it back to the very beginning of the stack frame. And then it also does pop EBP, which says, you know, the stack frame is usually pointing at a saved EBP for the previous stack frame, because they're that sort of linked list of stack frames. And so it does pop EBP, and then you're now, EBP is pointing at the next stack frame. And so typically you would see a return after that, but then the question is, what does the return actually do after you've done a leave? So you were on the right track before. Okay, so you'd said it goes back to where it's supposed to, right? So the return is actually, it assumes that whatever's on the top of the stack, that's a saved instruction pointer, and it just basically pops it off and sets the instruction pointer to that. So basically when you call something, the side effect is call instructions push the address of the next instruction onto the stack, and when you return, it's taking that thing which the call had saved there and popping it off the stack and going to the instruction after the call instruction, basically. Yep. All right, Reed, move and LEA.
Sure. So move lets you take a value in one register and move it into another register. Or you can,
Yeah, what were the three forms of move?
so you can do register, register. You can do memory address to register. I think you can also do can interpret value. You can do immediate to register as well, can't you?
Yes.
And I think
So-
for the memory address, it's actually you have to have the address stored in a register, and you tell the command to interpret
Right,
that address.
exactly. You're thinking of the square brackets, and we said last
Yes.
time, per convention, in Intel syntax, square brackets mean go to memory at that location. So you said store memory address into register. It's actually store the contents of memory into the register. So you take the
Yes,
address
I'm
in the EAX, you go to memory at that address, put it in the register, or take a register and put it in memory. So yeah, there were actually 4 forms. Memory to register, register, memory to register, register to memory, and immediate to register. Remember, immediate was basically a constant, which is just hard-coded into the instruction stream. So if you say move hex beef to EAX, you have the move instruction opcodes, and then you have hex beef in line. And then what about LEA? What's the difference with LEA versus move? First of all, what does it stand for?
That I'm not going to remember.
All right, Ariel. Nope. LEA stood for, okay, someone else. All right, yep, I think that was Jessica. Load effective address. All right, and so therefore, Jessica, what was the difference between LEA and move? In particular, we said there was a difference in convention, but you know, what does that mean?
I'm guessing, I admit it, but I think it's that when we LEA, we're dealing with the address, we're moving the address around. Move actually moves the value.
Correct, yes. So we said LEA was that one exception to that quasi-rule, which we were saying, if you see square brackets, that means go to memory. Whether it's move instruction, add instruction, pop instruction. If there's angle bracket, if there's square brackets around, you know, something, the instruction is saying go to, treat whatever's inside the square brackets as a memory address, go to memory, and then, you know, move that or pop it or add it, whatever. With LEA, we said in that case, since it's load effective address, it's more like you're doing maybe pointer arithmetic or something like that. And so you're saying, you know, take whatever's inside. Maybe you do that complex, you know, EAX plus 4 times EBX plus, you know, 32, something like that. Maybe you're doing a complex statement like that, but the stuff inside the square brackets is just ultimately treated as an address and moved, the result is moved in, and you're not actually going to memory at that location. So yeah, that's correct. Add and subtract or just add and subtract, right? But the only thing I would say is if we remember the bill over to the board, just as a reminder in terms of Intel versus AT&T syntax, if we were doing add EAX, that's not it. What is it? EBX, you know, how do we interpret this? What's going where? It's actually EAX equals EAX plus EBX, right? And it's actually the exact opposite of that on AT&T syntax, but we'll not worry about that. Right, so AT&T syntax flips stuff around, destination and source. All right. How about someone on the phone? Jump and JCC. What do those do? So first, jump. All right. Corey is saying jump changes EIP to the specified address after the jump. So what are the different forms of jump, Corey? We didn't actually learn this in last class, but we'll see. Yep, so far and short jump, depending on how far the address is away. So there he's saying there were different forms of jump. One of them will maybe use just 1 byte in order to say there's some address that's, you know, within plus or minus, well, whether it's in plus 128 or minus 127 bytes away. It can jump, I would say those are jump relative things. So there's jump relative things which say wherever I am currently, take the next address and add or subtract however many bytes. And that can be a one byte offset, or it can be a 4 byte. So that would be far or short. What else? Yep, you can do an absolute jump. So that's saying, you know, I'm just specifying here's the exact address I want to go to right now. And Corey is saying one more thing. Yep, so that's what Ariel just said. Dead beef can be, an absolute thing. And then actually, I would say there's also, there's indirect absolute. For instance, there's absolute where you're like putting an immediate, and then there's indirect where you're saying, here's EAX, and I want to jump to wherever EAX is pointing. And then there's actually an inter-segment jump, which we definitely didn't learn last time, but once we learn about segmentation today, I'll maybe remember to come back. But it's just saying all those other jumps are within the same segment, memory segment. So you got a chunk of memory, and it's all just bouncing around inside. There are actually other jumps which bounce you out to some other segment. So for what it's worth. All right, how about JCC, someone else on the phone? Do you remember what the point of that JCC mnemonic was? We don't actually see instructions called JCC, but what was that trying to imply? All right, yep, so David said it's jump conditional. So the CC was condition code. So give me some examples of different conditional jumps that we had seen. Yep, JNE, that was jump if not equal to, right? That was also called JNZ. So the issue with those conditional ones is they have typically like two names. So you can say jump if not equal, or you can say jump if not 0, because it turns out equality is just measured with the 0 flag. So in that eFlags register, we said there's a bunch of different little 1-bit fields which get set automatically on every single instruction. If they modify eFlags, they're always going to set those. And so jump not 0, jump not equal, it's really up to you to determine which makes more sense to you. Same thing with, you can say something is jump less than, or you can say jump not greater than or equal to, right? So there's like whatever, 4 pages worth of jumps if you ever want to look it up. I usually try not to care about what condition flags are set. I just use some simple ones like not 0, and if it's anything more non-obvious than that, like jump below or equal, or I'm trying to remember what is below versus less than, because one's signed and one's unsigned, I usually just go consult the manual or just step over the instruction and see where it went and say, oh, okay, that's what it was checking. All right, compare and test. Who else do we have that took the last class? Not seeing anyone else, but does anyone know on the phone what the compare and test instructions are equivalent to? We said that in reality they were like, compare is like one instruction, but it throws the result away and just sets the flags. Test is like another instruction, and it just throws the result away and sets the flags. All right, so we got Adam buzzing in. Handily consulting his manual out of sight. Yes, compare instruction is like sub-instruction. So it's like a subtract. It takes, if that add was EAX, EBX, we had if we had compare EAX, EBX, we would take EAX minus EBX, and then it would just set the flags based on that. So it's like if they were both the same thing, right, it would be A minus A equals 0. So the 0 flag would be set or something like that, right? So compare is just a sub. What about the test instruction? Anyone remember what that is? How about anyone in the room? A what?
And?
Correct. Yes, it is an AND instruction. There we go. Jessica got it as well. So test is just an AND instruction. So you do logical AND bitwise. You just take all the things, if 1 and 1, 1, all that sort of thing. If you had 0 and 0, then you would have, or 0 and anything, you're going to have 0 result, 0 flag would be set, etc. All right, good. Getting everything, and or, XOR not. And just, those are just your standard logical operations. What about this SHR, SHL, SAR, SAL? Yeah, Eric.
Those are the bit shifts.
Yep.
And I believe that the SHR and SHL move the bits and apply zeros. The other one rotates. And
not quite, but close, yes. So she said, yeah, correct. These are the shift operations, and they're bit shifts where you're taking, some bits and you're moving them left or you're moving them right. And then there was this difference between logical shifts and arithmetic shifts. Bill, can we go over to the board? So she was close. It wasn't quite a rotate where you would assume one bit falls off one side and pops around to the other side. It's close. Well, it's not quite like that. So how it works is, let's say I have EAX equals 12 or something like that. So that'd be 8, 4, 0, 0, right? So that's 12. I'm just going to pretend on a 4-bit thing here. If I was going to do a, if I took that and I did shift, let's see, let's do left, you know, 2, the 2 specifies how many bits to shift. The L for left shifts that way. And so in this case, I basically take each of these bits and move them left by 2. So this would, you pretend it's doing it like one at a time. And so it would go 0, 0, 0, 1, and then it would go 0, 0, 0, 0. And here you can see that essentially when we're shifting everything over, each time we fill the least significant bit in with 0. Now this is actually the case always for left shifts. Whether it's logical or arithmetic, that's sort of the redundancy, I don't know how you want to say it, but there's 2 instructions for it, but in reality they're both doing the same thing here. Any left shift, whether shift arithmetic left or shift logical left, it goes that way. The issue is when you're shifting right. This is where the difference between logical and arithmetic is. So if I have 1, 1, 0, 0, and I do a shift logical right by, let's say, 2 bits, what I would expect is it would go 0, 1, 1, 0, and then 0, 0, 1, 1, right? So this basically fills in, again, 0 is at the most significant bit. Now that's fine when you're dealing with unsigned numbers, but if we recall with signed numbers, the way that we break up the memory space is that there's always a 1 in the most significant bit of signed numbers. And so therefore, if you're doing this, and if this is, you know, not actually positive 12, but this is in reality, whatever it is, negative, thinking negative 3, or negative 4. Negative 3. All right, so if this were actually negative 3, and you're shifting right by 1 bit, which we know that shifting right is sort of like dividing by 2. Shifting left is sort of like multiplying by 2 for every bit that you're moving one way or the other. You don't want it to be the case that when you, when you're, is that right?
Don't you convert and add 1?
Yeah.
You're right, you're adding 1. But that was, let's see, oh, that's negative 1. There we go. It was negative 4.
Right.
Yeah. I was like, that doesn't work. Yeah, that was negative 1. That was negative 2. That was negative 3, negative 4. So, sorry. This is negative 4. The point is when you're shifting right, but you're negative 4, you don't want it to like, you want it to be divided by 2, right? If I shift it by 1, I want negative 4 to turn into negative 2. But, and we're going to change this to a shift 1 now. If we do a shift arithmetic left, or right, rather, you shift arithmetic right by 1, and this was the negative 4, you want it to be like this. It goes 1, 1, 1, 0, which, as we said over here, is negative 2. So everything works out in that case because we've always put a 1 in for the most significant bit when we're doing an arithmetic right shift. So that was, again, the difference between logical and arithmetic. Typically, logical can be used for unsigned numbers. Arithmetic has to be used for signed numbers. If you go back to the example 6 in the intro class, we had that one case where we just had, we're doing multiply and divide, and the compiler turned it into shifts. But if you change the variables from unsigned to signed, all of a sudden you get much more complex things that deal with arithmetic.
So does it actually always put the 1 in, or does it put in whatever the most significant?
Yes, sorry, yes.
Okay.
That was, I misexplained that. In reality, it always puts in whatever, at the time of the shift, whatever the most significant bit was, it always puts that in. So if this were some positive number like, you know, 0, 1, 1, 1, right? You don't want it like automatically adding a 1 because then it just completely changes it, right? So in this case, it would go 0, 0, 1, 1, and everything would still work out in positive land. Yes, thank you. All right, so that was the shifts. How about imul and div? Does anyone remember what was going on with those, what they are, and maybe a little bit about why we saw imul but not mul? And yes, as William said, for those shifts, one you always use for sign. Anyone on the phone remember imul versus div? I mean, should be obvious basically what they are. Anyone shout out what you think they are? Yes? What's imul? Multiply. Yes. What kind of multiply? That's what you're not remembering.
Signed multiply?
Yeah, one sign for
Yes. I believe it is a signed multiply, but even I'm forgetting that. So there you go. So if that's a signed multiply, then the div is an unsigned divide. The issue we had in the intro class was that well, it's not for whatever reason. We eventually found the reason. Someone found the reason, and I forget that as well. Visual Studio very much prefers the imul over the mul, so it always wants to use that, I believe, is signed multiply. But we can check quick because we still have the intro x86 slides on the desktop, right? There we go. Oh, maybe we don't. We don't have the slides. We just have the code. So let's look at the manual. RTFM, yo. Mul. Yes, signed multiply. There we go. For whatever reason, Visual Studio loves the multiply, and if we had our intro slides, we would know why, but I don't recall at the moment. All right, and then finally, rep stos and rep move. Well, I think the reason we saw it in last class was imul is a very special little instruction because it's like the only x86 instruction that has, or is that, yeah, the only x86 instruction that takes like 3 arguments for whatever reason. They have a 3-argument form. So let's see here. Take your destination is a 32, is a register. You got a 32-bit register. You've got an ARM32, which we said in the previous class could be that complex expression with the square brackets where it's, you know, it's base plus scale times, index times scale plus displacement, right? So that can be specifying some sort of memory address, but then you can also be adding in another immediate 32 in here. So the reason we saw it was because of that type of instruction. As for what it does that a mul doesn't do, I don't remember again. Sorry. I'd have to go check the slides. I'll check them at break, and I'll come back with an answer to that. All right, so rep stos and rep moves. Anyone here remember what the rep stos did? Saw it towards the end. It was one of the last instructions. It repeats something. All right, how about anyone on the phone? What is rep stos repeating? What sort of action is it taking? All right, Jessica's chiming in. Oh, Corey's taken over the lead. Oh, no, she already said it. Yes, repeat, store, string. Okay, so we saw like these 2 examples of repeat, and they both sort of had a similar mechanism where they were setting up some registers and doing something repeatedly. So Jessica, do you remember what registers rep stos was setting? And that essentially tells you, you know, what sort of storing it's doing? Like Corey's answer, some kind of string operation. Some kind of string instruction. All right, so yes, she's right that all the rep instructions use the EAX register. Are you like quoting me from the air there, or are you quoting me from the slides there? Yeah, that's what I thought. All right, so I'm just going to say what that does then, you cheater. Rep stos was repeat store string, over to the board, Bill. And specifically, we had seen it when we were looking at some Visual Studio code where we didn't turn off the one of its sanity check type, one of its sanity check options where it was checking the stack in order to look for corruption. Not in a security way, not like your GS stack cookie or anything. It was just trying to sanity check that there was nothing corrupt on the stack. And so rep stos, space there, it basically sets, you know, EAX equals count And that's the count of how many times you want to do the certain operation. So this will be either copying 1 byte or 4 bytes at a time, and the ECX is the count. So basically the instruction does this, this stuff. Does the store once, decrements ECX. Does it again, decrements ECX. So ECX keeps going down, and this instruction stops whenever ECX equals 0. Then it goes ahead and moves on to the next instruction. The other thing it had was EDI equal to the destination. Right? So wherever it's storing to this is wherever it's going to be storing to. So again, it's either storing 1 byte or 4 bytes at a time. And so if it's storing 1 byte, it takes EDI and it's saying, write 1 byte here and then move EDI, increment EDI by 1 byte, increment EDI by 1 byte, increment EDI by 1 byte. If it's doing a 4 byte thing, it increments EDI by 4 bytes each time. So write 4 bytes plus 4 bytes. Write 4 bytes plus 4 bytes. So keep in mind, these are different. ECX doesn't care what the size of the operation is. It just decrements by 1 every time. That's a count of how many times to do it. And EDI, it'll increment by whatever the size is because you're not obviously going to be wanting, if you're writing 1 byte, you want to write 1 byte like that. If you're writing 4 bytes, you want to write like that, right? You don't want to be writing 4 bytes like that, and then 4 bytes like that, and then 4 bytes like that. Maybe you do, but you're not. So finally, the discriminator here with repstos was EAX equals EAX, or let's call this parentheses around EAX, and actually that even doesn't work. It's either AL or EAX is the data to write at 1 or 4 bytes at a time. This question was, are those set up in previous instructions? And yes, anytime you see a repstos, you expect like pretty much immediately preceding them, there's going to be some move something to ECX. There's going to be some move something to EDI, move something to EAX, or they'll maybe move it to EAX, but it'll only be actually using the AL part of it. They'll lower. Remember we said for our general purpose registers, for at least 4 of them, they can be broken up like EAX, AX, and then A high and A low. So there's 1 byte A low, there's 1 byte A high, there's an AX for the entire thing, and there's extended EAX for all that. Right, so those get set up immediately before the instruction, and then you say, go ahead, repstos, go. And in reality, this repstos is going to look more like, repstos DS, which you don't know yet, but that's a segment register, DS, EDI, or something like that. And so it's really just saying EDI, write 4 bytes, write 4 bytes. And it's going to do this ECX number of times, storing to EDI, incrementing each time as it goes, storing whatever's in the AX or ECX. Now, having said that, does anyone remember what the difference is with rep move s? So we saw rep move s when we were searching for it, and where we were searching was in a memcopy. We were looking at the memcopy library code in Visual Studio's runtime C library. We dug into memcopy and we kept stepping into it until we eventually hit a rep move s. So the question is, if rep move s is like a memcopy, how was it different from this ECX, or repstos? Does anyone remember that? Anyone on the phone? Or he's taking a shot? All right, it comes from the value I'm filling in, instead of coming from EAX, is coming from memory as well. Where in memory as well is it coming from, Corey? ESI, that's correct. So, in rep move s, that's the same, but now this is ESI, which is the source, right? So we're taking from source, and we're going to go from memory. We're going to say take from source, copy to dest, EDI, and copy ECX number of times, and whatever size it is based on this. I didn't put in here as well, but in Intel syntax you'll maybe see something like byte pointer or like D-word pointer. That'll tell you what size it's actually doing. In reality, if we go fast in this class, we'll get to instruction size prefixes and stuff like that at the end, and then we'll be able to figure out by looking at the actual opcodes whether it's 1 or 4 bytes and stuff like that. But similarly over here, you have rep move s, byte pointer or D-word pointer. And then it's going to be doing something like ds, edi, and es, esi. It's saying from source to destination, right? We're copying from the right to left, as with all Intel syntax things. Go to memory at esi, grab out a chunk of memory 1 or 4 bytes big, copy it to memory at edi, 1 or 4 bytes big, do it ECX number of times, no matter what the size is. So this is, for instance, yes?
Jessica's got a question in the chat.
Okay, would you see this anywhere else but memcopy? You would, potentially, I mean, if you're writing your own memcopy, you would do this. If you go back to the Life of Binaries class, when I was writing the virus example, I used a rep move in order to copy the virus into the memory space of like some buffer which gets written. So the virus copies itself, so it points at its own code, copies its own code out to the buffer which gets written to the end of, appended to the infected file. Generally speaking, I would say that memcopy type places are the most you're going to really see this, other than inline assembly that people are writing. That's my own impression. I don't know if that's, I can't back that up with any numbers. So, but yeah, basically, that's where I would expect it to see the most. And then Mike, did you have a question or comment? Looks like, maybe. All right, well, he's typing. I'm going to finish this off. And then leave instruction we said before. Leave was really those two instructions combined. Move EBP to ESP, pop EBP. Yes, questions?
So in the example up there on the rep store S, AL would indicate a 1 byte move.
Yes, exactly.
On the other instruction, how would you indicate a 1 byte move?
Well, that's really, it ends up being, it's actually behind the scenes in the opcodes and prefixes which are used on the opcode. So the only way you can tell by looking at the instruction is whether there's a byte pointer included in the actual assembly that you're looking at. It'll either say rep move s byte pointer ds, and then you'll know it's copying byte at a time. Or it'll say d-word pointer, and you'll know it's copying 4 bytes at a time. That's how, and in AT&T syntax, it's a little different. I think they may have move sd or move sb or something. Yeah, you definitely have like move sb. So let's see what Mike was saying. All right, so Mike was asking, if copying from one memory location to another, isn't there a more efficient way to copy? Does this force the memcopy to copy all data through the CPU? Yeah. So if he's going, Mike, if you're getting for the point of, something like DMA, right? So DMA is direct memory access. And so if, peripherals or something need to move big chunks of memory around, the whole point of DMA is to cut the CPU out of the loop. It just it can just access memory directly and copy it to wherever else in memory it wants to. But yes, in answer to his question, this does go through the CPU, right? If you're doing a rep move s, it's the CPU going out and talking to memory and say, dear memory bus, give me this value, and then I want to go put that in there. And give me that value, and I want to go put it there. So it's definitely mediated by the CPU in this case. But if you were using something like DMA, that would not be the case. All right. That was it for our review. Any other questions on the instructions that we learned in the intro class? All righty. Now, I was going to quiz you, but I ran out.